Let's revisit our previous problem of transferring a spacecraft between two coplanar circular orbits. We have seen the Hohmann transfer maneuver where we use two impulses to move the spacecraft from one orbit to another. However, in certain situations, the Hohmann transfer may not be the most fuel-efficient method. We may choose another maneuver that uses less delta V but has three impulses. This maneuver is called the Bielliptic Transfer. Let me demonstrate to you how this maneuver works. The Bielliptic Transfer consists of two half-elliptic orbits. From the initial orbit, a first impulse expands delta V to boost the spacecraft into the first transfer orbit with an apogee at some point away from the central body. At this point, a second impulse sends the spacecraft into the second elliptical orbit with a perigee at the radius of our destination orbit r sub b. And here is where the third impulse is performed, injecting the spacecraft into the desired circular orbit B. Though the bielliptic maneuver requires one more engine burn than a Hohmann transfer, this maneuver requires a lower amount of total delta V than a Hohmann transfer when the ratio of the final to initial semi-major axis is 11.94 or greater, depending on the intermediate semi-major axis chosen. Starting from the initial circular orbit A, the first delta V puts the spacecraft on the first elliptical transfer orbit. The magnitude of the required delta V for this impulse is the difference between the perigee velocity of the first ellipse and the orbital velocity of the circular orbit A. When the apogee of the first transfer ellipse is reached at a distance r sub c from central body, a second delta V raises the perigee to match the radius of the target circular orbit B. This puts the spacecraft on a second elliptic trajectory. The magnitude of the required delta V for the second impulse is the difference between the apogee velocities of the two transfer ellipses. Finally, when the final circular orbit with radius r sub b is reached, a third retrograde delta V injects the spacecraft into the final destination orbit. The magnitude of the required delta V for this final impulse is the difference between the orbital velocity of the circular orbit B and the perigee velocity of the second ellipse. And the total delta V needed for the bielliptic maneuver is the sum of all delta V's, delta V1, delta V2, and delta V3.